Okay, so today we have the pleasure to listen to Spiridoula Matsika. She is a very important person in this field, and I'm sure most of you have already read a lot of papers from her work. And thank you very much for being with us today, Spiridoula. I know that everybody has been doing a lot during these crazy days. So I thank you very much for accepting the invitation and talk to us today. Spiridoula got his chemistry degree in Greece in 1994, and then she moved to the States for her PhD with Russell Pitzer. After that, in 2000, he did a postdoc work with David Yarkon in Johns Hopkins University. And since 2003, she is now in Temple University, where since 2014, she is full professor. And among a lot of distinguished, I select a few awards. As you can see, he got the National Science Foundation Award in 2005, Lovedin Lecture in 2012, a very prestigious series of lectures in Sweden. And this year, Holland organized another series of Lovedin Lecture. Alexander von Humboldt Fellow in 2013, American Physical Society 2014, co-chair of Gordon Research Conference 2016. So she is a very important person in this area. Her work is really very good. Among the research interests that she is carrying out, I highlight fundamental work with conical intersections and nonadiabatic effects. And if I'm not wrong, she was one of, among the first of, if not the first one to talk about free conical intersections in nucleobases. I think the work was with Uracil. Please correct me if I'm wrong, Spiridoula, but I think you were the first one to talk about free state conical intersections. And so thank you. So she is now working with designing more efficient fluorescence probes and controlling molecular photoinduced process with lasers, and of course developing methods and applications for electron-induced reactions. In numbers, I can say that she has around 120 papers, index age 13, and approximately 3,000 citations. So it's a great pleasure for us to listen to you today, Spiridoula. It's going to be very nice. So if you wish, you can interrupt Spiridoula to ask, and I do hope you enjoy her presentation. But please, keep your microphone mute, and if you want to ask, just raise your question, use this option in Google Meet room, and you can interrupt her, okay? So thank you very much, Spiridoula. I'm just going to close my presentation, and then you start yours. Thank you very much.
Thank you for inviting me, Antonio, and thank you for this very nice presentation. It was really nice, and I'm really happy to be here and talk about my work.
Okay.
So, all right. So everybody can see my slides?
Yes, I can see it. Yes, yes.
Okay, good. And you are going to, since I don't see anything, if anyone wants to ask a question, I cannot see anybody raising hand. So you will let me know if there is a question?
Yes, I'm going to control this section.
Okay, all right. Thank you very much. Thank you. All right. All right, so I'm really happy to be here to discuss with you some of the more recent work we have been doing involving excited states and conical intersections and all of these things that we have been studying for a long time. So I will start with the basic ideas on how we study excited states and nonadiabatic processes, and then I will move on to some specific systems that are teaching us something about dynamics in organic chromophores, which is very general. So if we want to theoretically study excited states for photophysics and photochemistry, pictorially, we have to look at the potential energy surfaces of molecules and build potential energy surfaces, find conical intersections, and see how the molecules evolve around these surfaces. In a more mathematical way, we have to solve the Schrodinger equation, and we solve the Schrodinger equation in two steps. In the first step, we solve the electronic structure of molecules, which is what gives us the potential energy surfaces, that they are felt by the nuclei. And then after that, we need to study the dynamics. So within the Schrodinger equation and beyond the Born-Oppenheimer approximation, the Schrodinger equation looks like this, where we have the motion of the nuclei on the potential energy surfaces. So the first line here is the regular Born-Oppenheimer approximation, but in this case is where we have to go beyond the Born-Oppenheimer approximation. We need to include these coupling terms, these additional terms that couple the potential energy surfaces. And specifically, what's of very importance is this F, which is the derivative coupling or the nonadiabatic coupling, which is responsible for coupling between the surfaces. Otherwise, the surfaces cannot go from one to another. So if we look at this expression for the derivative coupling, the superscript E here is the electronic energies and wave functions. So the denominator of the derivative coupling depends on the energy gap between potential energy surfaces. So the coupling becomes really strong when the surfaces approach each other, as we know, but we can see also mathematically. And in the extreme case that the surfaces become degenerate, then we have an infinite coupling. So that's why the conical intersections, which are the points when we have degeneracy, are extremely important for this type of processes because they have the most efficient way to couple potential energy surfaces. So just a slide about the conical intersections there because of their importance. So it was known for a very long time that the conical intersections can exist in an n-2 subspace. So if we have n degrees of freedom in our molecule, then we can have degeneracy in an n-2 subspace. This is because of the constraints we need to satisfy to have degeneracy. And that's when we have conical intersections. So the conical intersections are the points of degeneracy, but they are not just points, they're actually subspaces that we call sims, as you see on the second surface here. So in our job, we are looking for these conical intersections and we try to locate them to study molecules. But we have to keep in mind that they are full surfaces. And usually when we talk about conical intersections, what we report is the minimum energy on this sim surface. All right, so again, we study this problem in two steps. The first step is to do the electronic structure. And I'm not going to spend a lot of time on that here, just to give the basics. In the work that I will present today, the electronic structure is built from multi-reference electronic structure methods. So multi-reference methods are appropriate for this type of problems because they treat all the states equivalently. And that's why we choose this type of methods. And there is a variety of multi-reference methods, of course. Again, I'm not going to spend time here, but CAS-SCF is the first step always because it includes the non-dynamical correlation. But if we want more accurate results, then we can do it with multi-reference configuration interaction or with perturbation theory. So we have used all of these methods in the work that I will present, and I will indicate what we have used every time. So as a first step, we use some type of electronic structure method, and we try to study the potential energy surfaces. Of course, we cannot calculate the full potential energy surfaces for polyatomic molecules, but we can calculate important points. So the important points can be minima, transition states, and conical intersections, and that gives us information about the, let's say, the reaction paths involved in these types of problems. Now, the second step is, we don't always do the second step, but for much of the discussion I have today, we actually do the second step. With the second step is to do nuclear dynamics, so actually to see what the nuclei are doing and how they are moving around these potential energy surfaces. So as I said, we can do that with the Schrodinger equation, and that would be quantum dynamics, but this is quite expensive. So for the polyatomic molecules that we are interested in, it's actually not it's not possible to do quantum dynamics, including all the dimensions, all the degrees of freedom in the molecule. So instead, what we do is this semi-classical approach, which is called trajectory surface hopping, where we use trajectories starting from the excited state, and they evolve on the excited state using just Newtonian mechanics, but the forces come from the electronic structure. So the electrons are always quantum mechanically described. So we have the forces quantum mechanically, but then the nuclei move classically. And the only quantum behavior here is that when the coupling is sufficiently strong, then there can be a hopping to the lowest, or to a nearby state. And we do that with many trajectories which approximate a wave packet. So this is a very popular approach these days for polyatomic molecules. The advantage is that we can include all the degrees of freedom in our calculations, and we don't have to make a priori assumptions about what is important or what is not important, but the dynamics will tell us. Okay, so after this brief introduction of what kind of methodology we are using for our studies, I will go into the specific problems that I want to discuss today. And so I said organic chromophores, that is everything more or less. So the things that I want to discuss today involve, first I will discuss molecules that I have, dienes, so molecules with two double bonds, and some basic understanding that we have found recently about these molecules, especially about how these nonadiabatic transitions occur. So whether they are localized or delocalized in the potential energy surface. And then I will discuss another molecule which is more important biologically, which is work that we have done and Adonio has done for many, many years. So this is uracil, which is an RNA base. So I will also discuss recent work on the dynamics of uracil. And I don't know how time will be on the end, but I can say just a few words about fluorescent probes as well. All right, so so dienes. So starting with the basics. So what we mean by that is organic chromophores that they're conjugated and they have two double bonds. Okay, so butadiene being, of course, the prototype. And what we want to discuss here is we will compare basically molecules that they have the same chromophore, let's say. So these two double bonds are common in all of these molecules, but then the degrees of freedom that usually we don't consider as important for excited states are different, right? So here there's nothing, but here there is a small ring, and here there is a bigger ring. So the idea here is to see how this butadiene chromophore changes when we change the restrictions, or what these low frequency degrees of freedom, these other degrees of freedom exist in our molecule. All right, so to understand the basics of the excited states for these systems, I have a configuration diagram here that shows the states that they are important. So this is the ground state, and these are the pi orbitals, 3 of the 4 pi orbitals. So the HOMO -1, the HOMO, and the LUMO orbital. These are shown here for this molecule, which is cyclooctadiene, which is the one that we have actually studied in detail. All right, so what we have is that the first bright excited state is a HOMO to LUMO excitation, right? So we go from this pi to this pi star orbital, so this is pretty, I guess, common or trivial. But there is also a doubly excited state that is involved in these types of systems and in conjugated chromophores in general. And this is this doubly excited state with 2 electrons on the LUMO orbital. Now, this is not exclusively doubly excited, but there is a configuration mixing with other states as well, right? But this state is also relevant in the excited states and the dynamics of the excited states. Okay, so I will start very basic, right? So we're talking about double bonds. So I will start even more basic. Before we go to the 2 double bonds, I will remind everyone what happens when we have 1 double bond. So ethylene, of course, is the prototype for a single double bond. And in ethylene, once we excite ethylene, then there is a twisting along the double bond that will lead to an avoided crossing, right? So, and we can understand that because if we excite an electron to the LUMO orbital, then when we twist the pi and the pi star orbitals, they become more decoupled. So we can imagine that they will have similar energies at 90 degrees. But they don't cross. There's not a conical intersection at 90 degrees. But instead, in order to actually reach the conical intersection, we need an additional coordinate to move. So in addition to the twisting, we have this pyramidalization of one of the carbons, and that leads to the actual conical intersection. So of course, the ethylene has been studied a lot through the years by many groups. So here I'm just presenting pictures from Todd Martinez's work where they examined these conical intersections in detail, and and we see these 2 important degrees of freedom. So I am pointing this out because this twisting and pyramidalization is actually turns out to be important for many molecules that they have double bonds. It's not as clear as what we see here, but it is something that is common in all the organic molecules that they have double bonds. Of course, we will see it in the dienes, but we will also see it in uracil, which is a much more complicated chromophore. All right, so now focusing on the dienes here, well, what happens when we have 2 double bonds? So when we have 2 double bonds, well, we can simplistically think that we can think about the excited state mechanism to go back to the ground state. And again, these are simplistic, right? There are Rydberg states, things and other things that make it more complicated, but I'm only talking about the pi orbitals and the simple picture involving the double bonds. So, so if we have 2 double bonds, then we can imagine that we can twist one of the double bonds at a time. And then we have this ionic mechanism. And and this is ionic because when you twist and pyramidalize, one of the carbons has more positive charge and the other has more negative charge. So the pyramidalization creates an asymmetry in the 2 carbons, and the pyramidalized carbon will have more of a negative charge and the non-pyramidalized carbon has more of a positive charge. So that's true in ethylene as well. But since we have 2 double bonds, we can also imagine about twisting both of these double bonds at the same time and creating the products. Or you can also have a combination of those 2 mechanisms. So in butadiene, this is what's happening. There is a combination of those 2 mechanisms where either a single double bond is twisted or both of them are twisted. All right, so since I said we are comparing different molecules that they have this diene structure, these 2 conjugated double bonds, then the next system to consider is cyclohexadiene. So again, cyclohexadiene is a very well-studied system by many people and many techniques. It has been studied a lot theoretically, but also experimentally using any technique available. So here, because this is restricted, so the ring restricts the motion of the double bonds, the photochemistry actually involves this opening reaction. where the ring opens and gives the hexatriene. It also goes through the conical intersection, and it has been detected actually experimentally by electron diffraction that we go through this conical intersection, and then we create the cis and the trans products for the hexatriene. And this is a diagram of the potential energy surfaces that shows again that there is the bright state, but there is also this doubly excited state that is involved in the dynamics. So we didn't study cyclohexadiene in detail, but we did do the dynamics initially. It was more of a test for us to see that we are predicting what everyone else is predicting. So the results from our work are shown here. And this shows from the trajectories, so from each trajectory, we are plotting the C5C6 bond, which is the ring opening. And you can see actually from all the trajectories that about half of them open up and half of them don't open up, which is consistent with what is found experimentally. And we can also see that in the double bonds. So the double bonds, so if you look at one of the double bonds, it will become single bond in hexatriene. So again, you see a 50-50 or close to 50-50 actually, splitting of the trajectories for this mechanism. And this is the populations. So I show these plots. I will show these plots a lot here. So this is the population decay. So as a function of time. So in our trajectories, we count the trajectories and we measure the population, and we see how fast the population from the excited state. So here the excited state is the S1 state, the blue curve, how fast it decays. And this here is happening quite fast. So within 200 femtoseconds, everything has been moved from the S1 state. Because the second excited state is nearby, first there is some population that goes up actually to the S2, and then everything eventually goes back to the ground state. And this is happening really fast. Okay, so now the system actually that I want to spend more time is cyclooctadiene, which is shown here. So you can think of this as more flexible than cyclohexene, but more restricted than butadiene. And previously there was little known about this particular, the photochemistry of this system, but there is cis-trans isomerization as well, and there is also this photochemical product that has been seen and can be predicted actually with basic photochemical rules for the reactions. All right, so in our studies, we will do the excited state dynamics here to see what's happening. The first step in our calculations is to calculate the spectra using a Wigner distribution, which models the ground vibrational level. So that's how we create a wave packet on the excited state. So we sample the Wigner distribution and we create initial conditions for the dynamics. So we create a bunch of geometries for the dynamics, and we create a spectrum. And then using these initial conditions, we start the dynamics. So again, we did the dynamics for cyclooctadiene. Again, you see here the decay of the pi star excited state, which is similar to cyclohexadiene, right? There is a decay, there is some population of the S2 excited state, which is the doubly excited state, and then there is decay on the ground state. We could also, based on our trajectories on the ground state, we can find a distribution of different products. So we do have about 40% actually goes back to the ground state. We start with a cis isomer. About 40% goes to the trans isomer. So we have a cis-trans isomerization. And then we have some smaller actually products that we detected that probably they will not be, they're radical, so they will not survive for a long time in a real experiment, but we could see them in our calculation. So we have a 1,2 hydrogen shift, a carbon shift actually that makes a 7-member ring, and we also see this bicyclic product that has been seen before. All right, but what we want here actually is to look at the details of the dynamics. So this is a rough picture, but we want to look at the details. So again, there is this fundamental question: if we have two double bonds, do we expect one of the double bonds to twist, or do we expect both of them? So this shows, actually we found conical intersections that represent both of those possibilities. We found several conical intersections. And again, when I say conical intersections, this would be a local minimum on the seam of the conical intersection space. And we found several of these local minima. I only show 3 here, but we found even more. The basic characteristics are that in many conical intersections, only one of the double bonds is twisted at the conical intersection. But remember, in addition to the twisting, we have a pyramidalization. So when we have a double bond, we can pyramidalize the inner carbon, or the outer carbon can be pyramidalized. So this corresponds to different conical intersection structures, and we found them in our calculations. And then there are also conical intersections where both of the double bonds are twisted at the same time. And these are linear interpolations connecting the initial geometries, the Frank-Compton geometry, to the conical intersections. So you can see from the linear interpolations that these are barrierless, and this one has a small barrier, although this is an upper bound. This is a linear interpolation, so this is not, the barrier here is not necessarily as high as is shown here. But the linear interpolations help us get a more physical insight in what we see in the dynamics. So what do we see in the dynamics? All right, so first we look at this first question about whether one of the double bonds is twisted or both of those are twisted at the same time. And what we see is that, is everyone still hearing me okay? Hello?
Yes.
Okay, yes, I just want to, there is no background for me, so I want to make sure that, okay.
No, yes.
Okay, good. Okay, so, we are examining whether we have one of the double bonds, in what we see in the dynamics, in the trajectories that we run, whether one of the double bonds is twisted or both of them at the same time. So a good way to see that was to make this, this plot here where the dots represent, we look at the geometry at the hopping, right? So in the trajectory, we have hops, and that's what we can look at. The hops don't happen necessarily exactly at the conical intersection, and we have looked at that. So usually the hop from the excited state to the ground state will happen in the vicinity of the conical intersection, but not exactly at the conical intersection. But looking at these hopping geometries gives us information about the relevant conical intersections and the relevant reaction coordinates for the dynamics. So this correlation plot here gives us a first picture about whether both of the double bonds or just one of them is twisted during these hops. So what you see here is that it's more like a cross pattern. So a cross pattern means that only one of the double bonds is twisting at a given nonadiabatic transition, at a given hopping geometry. Of course, they're not exactly crossing, so there are some points here. So we use some arbitrary, threshold to count the hops that they happen where we can say that both of the double bonds are twisted, and we found that about 16% of the hops occur where both of the double bonds will be twisted, but most of them happen where only one at a time is being twisted. This is a different picture of this hopping geometry. So again, we're looking at the hopping geometries to understand better how the nonadiabatic transitions are happening. So now these are histograms. So we count how many hops happen for a given twisting angle. So this is a dihedral angle that measures the twist. And we look at the twist for each one of the, so I have two plots here. This is for the first double bond, and this is for the second double bond. Um, and what we see is that the value of this dihedral angle is actually quite spread out. So again, the message that we see here is that the hops not only don't happen at a minimum of the conical intersection seam, but also they happen at a wide out, so they happen at many different parts of the potential energy surface. So this dihedral angle has quite a spread of values where the hops are occurring. And we also looked at the pyramidalization, and we see similar things there. All right, so again, the important message here that I want to summarize in this slide that actually compares the hops to different molecules. So I have shown you already two, and this is the third way I show the same information. And the information is that the hops are very delocalized in cyclooctadiene. So, so here, now the gray lines are individual trajectories, and the dots are, again, where the hops are happening along the trajectory. And what we see in cyclooctadiene is that the hops are happening on a great variation. Again, the x-axis here is the twist. So this dihedral angle is spread out, and the hops are happening more or less at every value between -100 and +100, okay? So it's a very delocalized nonadiabatic transition process. Now, if we're going to compare this to other molecules, in cyclohexane, cyclohexadiene, I'm sorry, we are looking at a different twist, but we have looked at the double bond as well. And we see the same thing. So here you can see that the pattern is very different. All the hops are happening at very similar dihedral angles. So this is a much more localized process. And uracil, which is, I will talk about the dynamics of uracil later in detail, but here I only focus at this particular point, which is where do these nonadiabatic transitions to the ground state happen? And again, there is a double bond that is involved in the uracil dynamics, even though it's a much more complicated system. So if we look at when these nonadiabatic transitions are happening, at what values of this dihedral angle, we see that it is, again, localized. So this is, it's close to plus and minus 100 is actually, yes, closer to 90. So the sign changes, so you have the plus and the minus, but there's nothing in between. It's a very different picture from this, okay? So the overall...
Spiridoula?
Yes, yes. Mm-hmm.
Sorry, I think there is a question.
Yes, yes, sure.
Orlando? Orlando, do you want to ask something?
No, I don't want to ask anything. I'm just trying to figure out Spiridoula. I have to leave now.
Okay. All right. Thank you.
Well,
So I'm just trying to
congratulations,
figure
Roland.
out how to leave. I'm sorry.
Congratulations, Roland.
Yes,
Okay.
happy birthday, Roland.
Thank you very much. Thank
Nice
you.
to see you.
This is exciting.
Thank
See
you. Bye.
Okay, bye. So,
Okay, I'm
Spiridoula.
happy to, to entertain any questions at any point. Okay, so I really want to drive the point here that the dynamics for these other molecules are much more localized. So the twisting, which is the driving coordinate for this nonadiabatic dynamics, is quite localized. It doesn't take many values, but in cyclooctadiene, it is a much more spread out process. So we think that is very exciting. So most people, when they look at them, when they talk about the excited states of chromophores, they try to understand them in terms of the important reaction coordinates. So when we talk about conjugated systems, the important coordinates are the double bonds, okay? And there is actually, so Albert Stolow, who does experiments on these systems, he talks about a dynamophore. So a dynamophore here will be this conjugated system, right? So the important point is that usually we're always focusing on the double bond because that's where the excited states are happening, and that's what the driving coordinate is. The double bond is the twisting of the double bond, so that is really the driving coordinate. But what this says is that the other degrees of freedom, that they are not reactive, play some role. And it seems here that this flexibility and this additional number of low frequency degrees of freedom that exist in cyclooctadiene make it a much more delocalized process. Okay, so that is that is the I guess the main message that we learned from this work. And this can be important because it can affect the distribution of the photochemical products or the distribution of the energies at the end if we have such delocalized nonadiabatic processes. All right, so to convince you about this work, or to see that we really have a good understanding of this system, we are actually often collaborating with experimentalists, and specifically Tom Bynock is a long-term collaborator of us who does experiments, and they do pump probe experiments. And more recently, they are doing time-resolved photoelectron spectroscopy, which is a very useful tool to study nonadiabatic dynamics. So they applied time-resolved photoelectron spectroscopy on cyclooctadiene. And the cartoon here shows their setup. So they excite the molecules with 5 eV. It's closer to 4.7 actually. And then they are probing with an 8 eV probe. So the 8 eV probe ionizes the molecules, and then they are measuring the kinetic energy of the electrons that they are released, right? So if the molecule is ionized here with 8 eV proton, and this is the ionic state, the cation, then this extra energy will be released as the kinetic energy of the photoelectron, and this is what they are measuring, and this gives insight into the excited state dynamics. So this shows the spectrum that we have again, and this is where they are exciting experimentally. So we can use trajectories from this region to compare to the experiment. All right, so this is the photoelectron spectrum, and it's hard to interpret a blob, but by talking with experimentalists for a long time, we have also learned to appreciate what you can extract from this spectrum. So this is the kinetic energy, and this is, as a function of time, I'm sorry, I have cut the axis here, but it will be in the next. This is time, and this is the kinetic energy. So we can look at this two-dimensional spectrum, but then they also integrate different regions of the kinetic energy. So here, if you look at it closely, you can see that there are two features in the spectrum. There is a peak here, and there is a bigger peak here. So what they have done is they integrated the signal above and below this 1 eV threshold. And when you integrate the signal as a function of time, you see that the lower energy signal is more or less stable as a function of time, but the high energy signal comes down. It's hard to see in this picture, but if you integrate, well, you can see the boundaries, the green boundaries here. If you integrate, you see that the second signal comes down in time. Yeah, so I'm sorry, here is the time scale. Right, so this is our calculated time-resolved photoelectron spectrum. So we can calculate the spectra by if we have the neutral states and the cationic states, and then we calculate the probability for ionization, which is proportional to the Dyson orbitals, and we can calculate the spectrum as well, which we do, and it shows actually a longer dynamics than what they see in the theoretical spectrum. And this is also shown here. So we predict a longer decay dynamics compared to the experiment. But besides this quantitative disagreement, we want to see what else we can learn by comparing theory and experiment. So here I have, okay, so here I have the details again of the linear interpolations that I showed earlier. So this shows the conical intersections that I discussed, that, we have a conical intersection where it twists one of the double bonds or both of the double bonds. So we have these pathways. And now what we have done is we have added the cationic state. So the photoelectron spectrum will happen by, so there is a pump here and then the probe. So my red arrow here or purple arrow here is the probe. Right, so there is a probe that is going on at different times, and there are two signals that have been seen in the experiment, and the two signals come from those two states that they are highlighted, because those are the ones that they have the highest probability for ionization. So when we do the calculations of the Dyson norms, then we see that explicitly. So the two signals come from those two states. So we always start from the excited neutral state, but then we ionize to different ionic states, and we have two of them, and that's why we have two signals, two features in the photoelectron spectrum. Now we also see that this state is almost parallel to this state. Okay, so when the states are parallel, the photoelectron spectrum will not change. The kinetic energy will not change. Okay, because the states run parallel. But we also have this other state, which is anti-parallel to the neutral state. So when the ground state of the cation increases in energy when the S1 state decreases in energy. So what will happen then is that the kinetic energy released, which is this energy here, will start off being very high in energy, but then it will decrease in energy. Okay, and this is more or less what they see experimentally. So let me show it in more detail. So this is the calculated features. So here now I have calculated the photoelectron spectrum along this path, and you see there is one feature for all of these three pathways. There is one feature that is stable in energy, and then there is one feature that comes down. So those two features correspond to the two states that they are being ionized. Okay, so again, this is the experiment, and these are the calculations. So there is a feature that has the same energy, and there is a feature that comes down. So even though our calculations do not agree quantitatively on the time scales of the experiment, they agree qualitatively, and they tell us, they actually interpret the photoelectron spectrum. They tell us that what is happening is that the ionization occurs on those two ionic states, and that's why, and one of them is stable, has stable kinetic energy release, and the other one doesn't. So we think that this is a very good way to compare theory and experiment and learn more from each other. All right, so that is my story about cyclooctadiene and how the synergy between theory and experiment gives us this information about what's going on in the systems. So now I will talk a little bit about uracil, which is a more biologically relevant system. So group and many other groups have studied nucleobases, and the reason is because they're very important in the the interaction of DNA with UV radiation. So the nucleobases are the ones that they are absorbing the UV radiation. So this is the different absorption spectra for the bases. So they absorb around 260 nanometers. So that's very relevant for the UV radiation. And that's very relevant because the UV radiation can lead to DNA damage. So this is the photochemical reaction that is happening for the most common photochemical damage, which involves, well, it's not the most common photochemical damage, it's the most common photochemical reaction. So this is the thymine dimerization. So when two thymines are next to each other in DNA, then they will form this dimer, as is seen here in this crystal structure. And this, of course, can lead to mutations. But it is luckily it is being repaired by enzymes, even though it is happening quite often. All right, but what is also relevant is the photophysics. So the reason that this reaction is not happening very often is because the DNA bases are photostable. Photostable means that they have efficient mechanism to to relax and get rid of this extra dangerous energy. So this is a diagram from Bernd Kohler's review, who has done the initial experiments actually and a lot of work in this area, and shows the different timescales that they are involved for the nucleobases, or when they don't interact with each other, but also when they are stacked. So I'm not going to discuss anything about stacked here, although we have studied some of that. I'm only going to discuss individual uracil, but here we show the relevance. And of course, I should point out that there is a lot of work that has been done, and Antonio Borin, who is hosting me today, has been an editor in 2 books that they have summarized recently all of these developments, both theoretically and experimentally, for this very important topic. But today we're talking about basic features of the dynamics. So I will focus on uracil and some of the basic features of the dynamics. So it turns out, even though uracil has been studied extensively for the last almost 20 years, there are still some things that they are not settled or quite understood. And these are shown in this cartoon here. So in uracil, the bright state is the second excited state, which is a pi star state, and there is a dark state, an n-pi star state below the bright state. So the initial excitation leads to the bright state, which will decay through a conical intersection, and here it can either go to the dark state or go directly to the ground state. Okay. The issue that has been, I guess, controversial for some years is how fast the population on the S2 state decays through this conical intersection. And this has been controversially well, experimentally, people measure experiments, actually lifetimes. So I have the experimental lifetimes here. So there are some that they are just within hundreds of femtoseconds, and then there are some that they are a couple of picoseconds, and then something that is nanoseconds. So the experiments measure the times, and the times are what they are. The question is the interpretation of these time scales. Okay, so which of these times corresponds to the decay of the S2 population? And theoretically, so theory is the one that will help us in this area, and theoretically it turns out that there is a small barrier on the S2 state, and the value of this barrier, and whether the barrier exists at all, actually changes very much depending on the kind of electronic structure theory that we are using. So CASSCF predicts a higher barrier, but the other methods predict a lower barrier, and that of course changes the interpretation. Yes, and it will change the dynamics. So the dynamics most of the time has been done at the CASSCF level because it has been affordable to do. These are different, I guess, references and times and barriers, but I will not go into the detail. All right. So this is just to show what's happening in the dynamics. So this is the double bond. So I just want to point out again that even though this is a complicated molecule, you can see that the dynamics involves twisting around this double bond, as I was saying before. All right, so I will just talk about the dynamics that our studies. So again, we calculated the spectrum, and here we want to test the methods. So we actually did this for CASSCF, MRCIS, and XMS CASPT2, so different types of electronic structure methods, and even TDDFT. So we calculate the spectrum, and the spectra turns out agree better with the TDDFT spectrum agrees better with experiment. And then we find the conical intersections, and we build again these linear interpolations because they are easy for us to get a first glance of what's going on. So all of them predict a conical intersection between S2 and S1. Even here, you can see that the barrier is higher for CASSCF compared to these other methods. And then TDDFT actually gives a different pathway as well. It predicts a ring opening reaction, and that's what it does in the dynamics most of the time. So it's very different. And finally, the dynamics. So in the dynamics, again, we have the population decay. So we see the green line here is the S2 population, and we see that it decays with different time scales in the different calculations. So here, this is from an exponential fitting, so you can get an idea of how much this decay differs between the electronic structure theory, right? So CAS-SEF predicts a longer lifetime, but then these other electronic structure methods predict a much shorter lifetime. TDDFT predicts a shorter lifetime, but this is completely different. It predicts a ring opening reaction, which is not what is happening in the dynamics. All right, so now, okay, so we think theoretically these methods are better, but how can we confirm that? So we think that this is correct and CAS-SEF is not, but how can we confirm that? So now again, we go to our collaborators who do the time resolve photoelectron spectra, and we calculate the photoelectron spectra, and we see here the experimental photoelectron spectrum and the calculated ones. And it's hard to tell from the 2D, again, what is going on. So then we integrate in two different regions. So the top here, you can only concentrate at the top. So the top panels show the different methods, CAS-SEF, MRCI, and CAS-PT2. And the dots are the experiment, and then the red line is the calculation. So it's clear here immediately that CAS-SEF doesn't agree with the experiment. But the other two methods both agree with the experiment. So now we have an experimental confirmation that the S2 decay is really fast, okay? The experiments cannot distinguish between those two because the time scales are very fast and the time response of the experiment. So the time resolution of the experiment is not fast enough to be able to distinguish between those two. But we know that dynamical correlation is important, and CAS-SEF is not giving the correct answer. All right, so that's the second lesson that I am, in addition to studying uracil, the second lesson here is that the electronic structure method can play a very important role in the dynamics, but that is not always the case. So in uracil, that is absolutely the case. So we really need dynamical correlation. But for these other molecules that I talked about, it doesn't make a difference. CAS-SEF is perfectly fine. So one should be careful about the choice of the electronic structure, but it's system dependent. So one should check for a particular system what works. All right, so I think I will, so here I summarize what we learned about the dynamics of organic chromophores. And we learned that we can study the radiation-less decay, of course. And the first lesson we learned from COD is that these low frequency degrees of freedom can be very important, something that we have not appreciated so far. We also learned that electronic structure is very important. The choice of electronic structure is very important, but not for all molecules. So we have to be very careful how we choose the methods. We learned that the S2 decay in uracil is actually very fast, much faster than what CAS-SEF has been predicting. And that when we combine theory with detailed experiments, so we have a detailed comparison between theory and experiment, we can actually learn a lot about both. So we can benchmark the theory, but we can also interpret the experiments. So I will stop here. I will not talk about fluorophores because I think I have exceeded my time. And I will just thank my group for all this work. This was just before the pandemic. Pratip, who is over here, he just graduated actually, but he's the one who did all the dynamics that I have discussed. This work has been funded by the Department of Energy, and these are my collaborators for the time result experiment. And I thank you very much for your attention. And I will be happy to take any questions now. Thank you.
Thank you, Spiridoula. Very nice talk. Thank you very much.
Thank you.
And I think we already have a question from Mauricio Coutinho. Please, Mauricio.
Hi. Very nice talk. Congratulations.
Thank you.
For the work. So I have two questions. The first one is concerning the number of trajectories that you need in order to reach conversions, and if that's system dependent. And the other one is concerning the last topic about testing the methods. it seems that if you rely on the absorption spectra, that's not a very good no, that's not a very good measurement. So do we have any other quantities to look after?
Yes, yes. So I will start with the second question. Yeah, you're absolutely right. So I think it is spectacular actually to see the good agreement, the perfect agreement of TDDFT absorption spectrum, which is often true, but then that it doesn't predict the correct dynamics. So I think it's hard. Yeah. So then you don't want to do all the dynamics to test every time which method is appropriate. So I would think the linear interpolation, so finding the conical intersections and calculating the linear interpolations are better in giving us an idea of which methods will be appropriate or not. So in uracil, for example, even from the electronic structure, even from the linear, or are actually calculating the barriers, we can already see that the barrier calculated at the CAS-SEF level is higher than the other methods. So that's already an indication that the dynamics will be different. So that's what I think. So yes, absolutely. The absorption spectrum is not enough, but having an idea of how the potential energy surfaces look towards the conical intersections should be much more important. I should also say that it's actually even more, so even within CAS-SEF, how many states you average, what is your active space, all of these things change the barriers. It's actually really tricky. So all of these things should be tested. The other question about the number of trajectories, that's also a very good point. So I didn't say much about how many trajectories we used and so on. Because so when we did CASPT2, these are very expensive calculations, so we cannot afford to do as many trajectories as before. So I cannot say we have benchmarked it for everything. So for the results I showed, it was maybe 100 trajectories that we have used.
Okay.
So I think that would be a
good starting
number.
point.
I wouldn't say it is, yes, it's a good number. So for CASPT2, we can see that we have less than 100. Probably we have 50 there, and you can already see that if you look at the populations, they're not as smooth, and they can change.
Okay. It's very nice.
Thank you.
Other question, please? Mauricio, do you want to ask something else?
No. I'm fine.
Anybody else, please? Sinara, okay, please ask him. Sinara? Oh no, it's not Sinara, it's Lucas. Sorry.
Lucas, yeah, I saw Lucas.
Okay, Lucas, go ahead.
Thank you. Thank you for your presentation, Dr. Spiridoula. I have a question because I was looking for your results concerning the last part of the lecture, and I've seen that TDFT predicts a break of the bond. Is it a case where the TDFT doesn't work, or is it a problem related to the methodology that will always happen when we do this kind of study?
You mean, okay, so so I am not fair to TDDFT here. We only tested one functional. We really didn't try to see how well TDDFT can predict that, okay? So we just tested the B3LYP functional because everybody is using it, and we found these results. So I think a more appropriate, so I don't know exactly what the problem is. I think a more appropriate study would be to actually use different functionals and study more carefully exactly what is happening and why it's happening. And we have not done that. So I'm not as fair to TDDFT here. So I don't know which part is actually to blame for this behavior. So in the multi-reference methods, there are maybe one or two trajectories that do the same thing, but definitely not the majority. So in TDDFT is actually the majority of the trajectories that do that.
Oh, okay.
And again, it could be the functional. I'm not sure what it is.
Okay. Okay. Thank you.
Mm-hmm.
Any other question? No? So I have some.
Good.
Have you tested other single reference methods, for instance, ADC2 or, I mean,
That's a good point too. Yeah, we tried to do ADC2. There were technical problems, so we didn't actually. I think ADC2 has been used for nonadiabatic dynamics of thymine at least, and we did try to use it, but then there were technical issues, and we didn't try to pursue it further.
Okay. And about the TDDFT, do you think that the multi-configurational version of LaURA would do a better work? Multi-configurational pair DFT?
Yes. Okay. I don't know, because I don't know what's the problem, right? I really don't know what the problem is for the one we did. In general, it should be better for the nonadiabatic effects, but in this particular case, I'm not sure why it goes to this, because this is it's not. So of course, the regular TDDFT will not work for hoppings to the ground state, but this is happening already between the S1 and the S2, so it's already going in the wrong direction early on. So again, I'm not sure what the problem is.
Yeah. And
to say what will fix it.
Do you have any hint about the problem with dynamical correlation effect? Because it works sometimes it's necessary, in other cases it's not. Do you have any hint about the kind of systems or the structure where the dynamic correlation effect would be more important? Just looking at the system?
Yeah, that's a good point. I don't. I mean, uracil, the S2, I know for uracil that the S2 is very sensitive and very difficult to calculate appropriately. But it would be nice to be able to generalize. You are right. It would be nice to actually look at the system and have an idea. But unfortunately, I don't have a good insight. Yeah. I guess if we do more systems, we could try to get a better idea, but at the moment I don't.
Okay.
But it's very, I mean, I was impressed though that for CHD and COD, they were identical. They were almost on top of each other. And for COD, we were hoping that they would be different, because actually COD doesn't agree with experiment, but the time scales don't agree with experiment as well.
Okay.
But yeah.
Another question, I don't remember, but what kind of which program have you used for the CASPT2? It's OpenBookhouse.
No, this is Bagel.
Oh, okay, Bagel. Yes.
I guess I should reference the program.
Yeah.
So we use Bagel.
Yes, it's analytical gradient. Yeah. So okay, I forgot it. Sorry. Okay. So there is another. I think we have two people. Well, Ignacio, there is another one before Ignacio, I don't know. Max, yes. Max Pinheiro, please.
Hi, Spiridoula. Thank you for the very nice talk. It was wonderful.
Thank you.
I have just I'm curious about one point. It is sometimes when you have like flexible systems that can take different pathways during the dynamics, maybe it's difficult to just separate those trajectories that are similar to each other by eyes. So my question is, I'm curious if you are using some kind of clustering method, some kind of analysis to have some statistics of how many trajectories go to one path compared to the other one, especially for this kind of more flexible system that have more complicated pathways during the dynamics.
Yes. So that's important for cyclooctadiene.
Yeah.
So there the branching to the photochemical products was very easy because there you can actually see it by eye. So the difficult part was the different conical intersections. We didn't try, I guess, very sophisticated analysis. We try to do something beyond just looking at them, right? We try to look at, clustering the different degrees of freedom, but not, I guess there are more sophisticated methods that we haven't tried. At some point we gave up. There were so many conical intersections doing different things that we thought it was actually, the main point was that it was so delocalized. So it was more important to focus on that rather to try to break it down. But I know there are more sophisticated ways to do this. But I don't know what, I mean, we looked at whether one bond twists versus two. But beyond that, I don't know exactly what would do to actually try to cluster them even more. For me, it's really important that actually it is such a delocalized problem.
Yeah, I think it's a bit tricky and a challenging thing to cluster time series, because in the end, the dynamics is just a time series. Yeah, but thank you for the answer. Yeah.
Thank you.
Sebastian, would you like to ask something? You open your camera.
There was just more a comment on your question when you said that some systems work with CF and some don't. It could have something to do with whether you have different kinds of electronic states inside your dynamics or not. Like in the dienes, in the COD and so on, you're essentially only having star states, which all suffer in the same way from the bad treatment. While on uracil, you have n-pi star states that work well with CF and pi star states that don't.
Right, that's a good point. But yeah, you are correct in that. But I think in uracil, the problem is not, the problem is even just looking at the S2 state, the pi star state itself, that it is really problematic. So I don't know if the n-pi star, so the imbalance between n-pi star and pi star will have an effect of the crossing, I guess. But yes, here, I think it's more than that. I think it's this barrier on the S2 surface that plays a big role. But you are right overall. I think overall it's true that if you have states that they are treated differently with dynamical correlation, that will be one way to figure out that dynamical correlation is important.
Yeah. And otherwise, I also liked Antonio's suggestion about the MCP DFT, because actually just this week we also realized that they have gradients, and we will start looking into that with Shark and whatever future projects we might have. So if they give nice surfaces, then surely we will also have a look there.
Yes, I agree.
Yeah. Otherwise, thanks for the talk. It was very nice.
Thank you.
Looked very familiar, at least some parts, because it's exactly what we're also doing: excited state potentials and dynamics and surface hopping and so on. So yeah,
I think Patrick has been discussing with you sometimes, right?
Yeah. This was like 7 years ago in this conference in Graz.
Oh wow.
This was when we met, I think, and discussed quite a lot. But since then, I think. A lot of things happen.
Yeah.
So thanks.
Thank you.
Thank you, Sebastian. There is another question, I think, who is going to ask? I think it's Julio Cesar, okay? Julio, you?
Okay. Hi, Spiridoula.
Hello.
Okay, I would like to thank for presentation, first of all. Nice. Was very nice. I have a more general question. I saw you are interested also in transient negative ions, right? I saw some works about it, and I would ask you if you are interested in perform dynamics with transient negative ions, because in this case we don't have a spin orbital complement, for example, but we have the auto detachment channel, and it could be easier for one hand, but on the other side could be much more hard to perform it.
Yep. I agree. Yes, that's the long-term goal to do dynamics on the transient negative ions. So we are at the moment we are still exploring the best way to get the energies and the lifetimes, the widths. The lifetime. I mean, doing dynamics correctly will be very, very challenging. I think we can do some qualitative things with dynamics where we don't worry very much about, I mean, where we do them separately, right? Where we do the dynamics on the surfaces and then we calculate the lifetimes for each time step. But incorporating everything together is really, really challenging.
Okay,
but yeah, yes. Eventually we want to be able to do some kind of dynamics for the systems.
Yeah, nice, because I think will be necessary to implement some auto detachment channel on the fly, or after the calculation, maybe, I don't know.
Yeah.
I would ask you to about the computational effort for this calculation, because in fact I would like to ask you about the kind of high computing you have in your group of research, you know?
Yes, okay, yes. Computing is a big problem, especially when you want to do caspity dynamics. I think Pratik knows much better the pain of that. So we are actually for these dynamics we used XSEED. I think I had it in my acknowledgement. So this is a national service where they have computing facilities in different parts in the country, in the US, and you apply for a grant and they give you time to run. So we were using these big nodes. I don't remember exactly what the specifications were, but these are nodes with thousands and thousands of processors. And that's how we were able to run. So we were not running them locally on our computers.
Okay, nice. Well, thank you so much again for presentation, for answers.
Thank you.
Thank you, Julio. Now there is another question. Danilo, please.
Hi, Spiridoula. Thank you for the presentation. Very good. I appreciate it a lot. My question is about how the choice of the active space in the multi-reference method affects the nonadiabatic dynamics. Because I think that in MRCI, you are using a reduced active space. And another question is if you have ever included the triplet states in your dynamics for yourself, for example.
Okay. So the second question is easy. No, we haven't included triplet states. Triplet states are important for uracil. The triplet states will be important later. So we were just focusing on the S2 decay, but if one wants the complete picture, then the triplet states. So I guess Sebastian and Leticia Gonzalez have looked into triplet states and they know their importance better, but we have not done it. So we have avoided the triplet state by focusing on a very specific problem. It would be nice at some point to do triplet states, but we haven't done yet. The active space indeed is important. I'm not sure if you were asking about the performance overall or about how the trajectories fail. So it is true that trajectories will fail eventually, especially when you go into the ground state, and we try to be very careful about that. So if they fail on the ground state, it's not such a big problem because they have already decayed in the ground state. And that depends on the choice of the active space. So Pratik did a more careful study on cyclooctadiene, and actually initially he was using a different basis set, a different active space that seemed to be more accurate for the excitation energies, but it was behaving really bad during the dynamics, and we had to abandon that. So it's true that we have to be careful about the active space, and just by looking again at the absorption spectrum or the excited states initially vertically doesn't give you a good idea what will happen later.
Okay, thank you.
Thank you, Danilo. Any other question? No? So I thank you again, Spiridoula. It was a very nice talk, and you, by the many questions you have answered, you see that you caught the attention of many people. Thank you very much. It was very nice talk.
I really enjoyed the interaction. Yeah.
Thank you very much. And I hope to meet you again in the next seminar. I'm going to send you all the link for the invitation for the next seminar. It will be in April, I don't know, let's see, April 9, I think. Well, but next week I will send you the...
Okay, thank you. Yes, I will. If I am available, I will definitely try to come. This is great. I really enjoyed the questions and the interactions. I thought that was really great. Thank you.
It's very informal, but I think that's the way I think it should be. So everybody has the opportunity to talk and to ask. Thank you very much, Spiridoula.
Thank you. Thank you.
So
thank you, everyone.
Okay. Thank you, everybody. So I think it's time for lunch now.
Okay, yes.
Dinner for me.
Oh, not for you. It's for dinner. It's dinner for you,
yes.
Can you satisfy my curiosity, Antonio? Who will be next?
Who? Laura Gagliardi.
Oh, nice. Very nice. Yeah.
Thank you, everybody. See you soon.
Thank you.
Be safe.
Thank you. Very nice series. Thanks. Bye.
Bye.